Okay, in this lesson, we're going to look at more methods of proofs. These are going to be sort of the indirect proof methods in a lot of cases. In the previous lesson, we looked at the concept of direct proof, where we started with the hypothesis and then using theorems, definitions, etc., we were able to create an argument or a proof of the conclusion. So we're going to add to our tool set of how to prove things in this lesson. First thing we're going to look at is proof by contradiction. So a proof by contradiction will establish P implies Q by assuming that the hypothesis P is true and the conclusion is false. Then by assuming the conclusion is false, we'll use the proposition P, which is true, and Q and not Q, which would be false, as well as other axioms and definitions and such to show that a false conclusion leads to a contradiction of the hypothesis. Okay. Recall that a contradiction is the propositional form R and not R. I used R, but you could use any of the letters. It's basically a proposition and with its negation. Will always be false. Okay, this statement will always be false regardless of whether R is true or R is false. A proof by contradiction is often referred to as an indirect proof because it establishes the proof of P implies Q using the contradiction of Q. And we follow an indirect route to get to the conclusion that Q is true. And the way we do it is we derive a contradiction and then conclude Q is true. So you assume Q is false, you work through what that means, you work through what Q is false tells you, and then you end up deriving a contradiction. So what we're using is this fact, that P implies Q is logically equivalent to P and not Q implies a contradiction, R and not R. So notice Q is a statement we're going to assume the opposite of Q. We're going to AND it with P, and we're going to say whatever that is implies a contradiction. So to show that's true, you'll just prove it with a truth table. So since I have three propositions, P, Q, and R, I've got an 8-row table. So recall the way we lay them out is true, true, and true, 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 and false, true, false, and true, true, false, false. And then we set P to false and repeat the Q and R. So you got false, true, true, false, true, false, 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 true, false, false, false. So notice I'm going to need not Q. So if Q is true, true, false, false, then not Q is false, false, true, true. Okay. If Q is true, true, false, false, then not Q is false, false, true, true. So that's that column. Not R. If R is true, not R is false. So you see true to false, false to true, true to false, false to true. And likewise here, true to false, false to true, true to false, false to true. So now I'm going to AND P and not Q, right? So true and false is false, true and false is false, true and true is true, true and true is true. The rest are false because P is false, so it doesn't even matter what not Q is. Okay, so there's that column. Then we're going to do R and not R. Since that's a contradiction, it's going to always be false. So now we do P implies Q. True implies true is true. True implies true is true. True implies false is false. True implies false is false. Since P is false, all the rest will be true. Okay. So now we're going to do P and not Q implies R and not R. So in other words, right here, these two rows. So false implies false is true. False implies false is true. True implies false is false. True implies false is false. And then since P and not Q is false the rest of the way down, then all the rest will be true, right? Because false always implies true regardless of what the second thing is. So notice they're exactly the same. True, 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 false, 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 true, 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 true. So that proves this logical equivalence. Okay. So let's look at an example of how we use this proof by contradiction in a real proof. So, for example, we're going to give proof by contradiction for the following statement. For every n in z, if n squared is even, then n is even. Now, if you try to do a direct proof, we assume n squared is even, and that means n squared can be written as 2k, where k is an element of the integers. Okay. But there's not really an easy way, based on n squared being 2k, to show that n is an even number. So we would need to show that n is 2j, where j is an element of z, and that's not easy to show, because what I'm going to do, if I take the square root of n squared, I'm going to get square root of 2k. Square root of 2k can't be written as, can't be easily shown to be an integer. I mean, can't be easily shown to be an even integer. So what do we do? Okay. So we'll use the proof by contradiction. Okay. Proof by contradiction. We're going to assume n is odd. Why? Because that's the opposite of what we're saying. So remember, it's if p, then q. So q is n is even. We're going to assume not q. N is odd. Then we'll take, what does that mean? N is 2k plus 1, where k is an integer. Okay, that's what it means to be an odd number. Now let's look at n squared. N squared is going to be 2k plus 1 squared. N squared equals, if 4k squared plus 4k plus 1, because I just squared out this binomial. Okay. Now what I'll do is I'll group the first two terms together and factor 2 out of the first two terms. So notice n squared can now be written as 2 times parenthesis 2k squared plus 2k plus 1. Well, if k is an integer, so is k squared, so therefore so is 2 times k squared, and so is 2k, so I got an integer plus an integer is an integer. So basically, this n squared can be written as 2 times an integer plus 1, which is our definition of an odd number. And that's our contradiction, because our hypothesis said n squared is even. So by setting n to odd, we showed that n squared is odd, but n squared can't be odd, because we've said it has to be even. So that means n can't be odd, because if n was odd, n squared was odd. So that's our contradiction. So since n can't be odd, it has to be even. So that's how contradiction works. We assume the opposite of the conclusion, and then we try to contradict the hypothesis. And if we do, then that means the conclusion can't be the opposite. It has to be what we originally thought. And that's exactly what we did here. Here's another one we can do. Prove that for all x in R, if x cubed is irrational, then x is irrational. So we're going to do this by proof by contradiction. We're going to assume the opposite of x is irrational. That means we're assuming x is rational, because that's the negation of x is irrational. If x is rational, you can write it as a fraction p over q, where p and q are elements of the integers. So now we'll cube both sides. X cubed equals p cubed over q cubed. Okay. And of course, p and q are element integers. So if p and q are element of integers, so is p squared cubed and q cubed. So this means x cubed is rational. Okay. But that contradicts our hypothesis that x cubed is irrational. Okay. And thus, x can't be rational. But if x can't be rational, it's therefore irrational. So we've proved it. We proved that if x cubed is irrational, then x is irrational. One famous proof goes back to ancient Greece or something, is the proof that square root of 2 is irrational. And it's done by contradiction. What are we contradicting? So the conclusion is root 2 is irrational. So we're going to assume the opposite. We're going to assume that root 2 is rational. Then, if that's true, there exists a p and q such that root 2 equals p over q, and of course p and q are integers. That's what it means to be rational. We're going to assume p over q is in lowest terms, which means both p and q can't be even. Okay. So now what we'll do is we'll take this, our definition of root 2 equal p over q, we'll square both sides. And that gives you 2 equals p squared over q squared. Okay, no problem there. Now we'll multiply both sides by q squared. And that'll give us 2q squared equals p squared. Okay. Now recall we already proved that the square root, that if a square of a number is even, so is the number. So this follows from our first example that if p squared is even, then p is even. Okay. Therefore, there exists a k such that p equals 2k because p is even. That's our definition of even. So we're going to go to this formula, 2q squared equals p squared, and where there's a p, we're going to substitute 2k. So that's what's done right here. Okay. So now you have 2q squared equals 2k quantity squared, which is 4k squared. Okay. So notice now I could cancel 2 on both sides. So I divide 2q squared by 2 and 4k squared by 2, and I get q squared equals 2k squared. If k is an integer, so is k squared. So q squared is 2k squared. Therefore, q squared is even, and thus q is even. So now I've got p and q are both even, which contradicts our hypothesis that p over q has to be in lowest terms. If both are even, then p over q is not in lowest terms because you could divide 2 out of each one. So that contradicts some of the p and q are not both even. Therefore, I can't assume root 2 is rational, and it has to be irrational. So that's the proof. You now know for sure for the rest of your life that the square root of 2 is an irrational number. Okay. The next indirect proof style we're going to do is something called proof by contrapositive. Okay. So recall from our discussion from the propositional logic section, the conditional was denoted P implies Q, P arrow Q. Also recall that the contrapositive was denoted as the negation of Q implies negation of P. Further, we proved using truth tables that P implies Q is logically equivalent to not Q implies not P. So let's replicate that proof. Okay. So to create a truth table to show that this logical equivalence is true, I created a table where I had, only had 2 base propositions, P and Q. Notice I needed not Q and not P, so I created a not P and a not Q column. And then a P implies Q and a not Q implies not P. So since I got just 2 propositions, I'll fill it in our normal way, true, 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 false, false, true, false, false. Okay. Now P is true, true, false, false. So not P is going to be false, false, true, true. Okay. Not Q is going to be true. Since Q is true, not Q is false. Q is false. Not Q is true. Q is true, not Q is false. Q is false, not false is true. Now we have P implies Q. P implies Q, is going to be true. True implies true is true. True implies false is false. And then false implies true is true. False implies false is false. Okay. And then not Q implies not P, which if you go to these columns, you'd be doing the not Q implies not P. So you look at false implies false is false. True implies false is false. I'm sorry, false implies false is true. False implies true is true. True implies true is true. And notice these 2 columns are the same. They have the exact same truth values for every row. That means that these 2 statements are logically equivalent. So this just replicates our proof of this that we did earlier. Sometimes it's easier to do a direct proof on the contrapositive than it is on P implies Q, on the original conditional. Since the two are logically equivalent, using a direct proof on the contrapositive will also prove the conditional. That's why it's useful to do this. So let's go back and do that same proof we did with contradiction, but now we'll use contrapositive. Okay. So here it says, give a proof by contrapositive to prove that if x is in R, or for all x in R, if x squared is irrational, then x is irrational. So our original conditional, P implies Q, P is x squared is irrational, then Q is irrational. So what we're trying to prove is this, P implies Q. Notice the negation of P is x squared is rational, and negation of Q is x is rational. So if I prove this, negation of Q implies negation of P. If I can prove this with direct proof, then by logical equivalence, I've approved the original. Okay, so if x is rational, right, then x squared is rational. That's the contrapositive. And this is the statement we're going to prove. Okay. So if x is rational, then x can be written as P over Q, where P and Q are elements of the integers. Therefore, x squared can be written as P squared over Q squared. Okay. Since P and Q are integers, then P squared and Q squared are integers, which means that P squared over Q squared is a rational number, which proves the contrapositive, right? So I prove the contrapositive. If x is rational, then x squared is rational. Since the contrapositive is logically equivalent to the conditional, in the original conditional was if x squared is irrational, then x is irrational, is also proved, right? That's the whole point behind it. If I take a conditional and I write the contrapositive and then I use direct proof or any kind of proof method to prove the contrapositive, I've automatically proved the original conditional because they're logically equivalent. Logically equivalent means they're the same statement. Okay. Another proof thing is proof by cases. Okay. This is used when the original hypothesis could naturally be divided into various cases. For example, the hypothesis x is a real number can be divided into cases like x is a non-negative real number and x is a negative real number. Suppose that the task is to prove P implies Q and that P is equivalent to P1 or P2 or P3 all the way up to Pn. And P1 up to Pn are cases instead of proving P1 or P2 or P3 or blah 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 down to Pn implies Q. We can say, well, that's just, the same thing as saying P1 implies Q and P2 implies Q and da 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 down to Pn implies Q. So in other words, you take each case, you break it up into cases, and you prove each case implies Q. And if they all work, then you've proved the thing. That's called proof by cases. So a kind of a nifty example of proving something by cases is this one. It says I want to prove that 2x squared plus 3y squared equals 40 has no solution in the positive integers. Okay. So that is 2x squared plus 3y squared equals 40 is false for all positive integers x and y. Okay. So he says positive integers, so he's meaning he's not including 0 and he's not including negative integers. So we just want to show it's true for all positive integers, that there's no solution to this equation. Remember, a solution is a value for x and a value for y, that if I plug into the equation, it ends up equaling 40. So to do this, we're going to generate cases based on values of x and y. Okay. So first thing I'm going to do is say, well, let's take y, set it equal to 0. Okay. And then that means I have 2x squared plus 3 times 0 squared is 40, which means 2x squared is 40, which means x squared is 20, which means x is 2 square root of 5. Okay. Now, 2 square root of 5 is bigger than 4, less than 5. It's not an integer, but it falls between 4 and 5. Okay. So since I'm only plugging in integers, if I take 5 and plug it in for x, I'm going to get 50, right? And regardless of what y is, plugging 5 into x gives me 50, so I'm already too big to be a solution. Okay. So any value greater than 4 will give a value larger than 50. So I know right now x, regardless of what y is, x has got to be 1, 2, 3, or 4. If it's 5, it's too big. It doesn't, and since we're not allowing for negative, and it wouldn't matter if we had negative, but once x is 5, it's the 5 squared is 25. 2 times 25 is 50. It's already bigger than 40, and no matter what y you plug in, you're still going to be bigger than 40. So anything bigger, x having anything bigger than 5 will never generate a solution to this equation. All right. Now you do the same thing. We'll set x equal to 0. We'll have 2 times 0 squared plus 3y squared is 40. We'll divide both sides. So that means 3y squared is 40. Divide both sides by 3. Y is square root of 40 over 3, or 2 root 10 over 3. 2 root 10 over 3 ends up falling somewhere between 3 and 4. Okay. So if I plug y equals 4 into this equation, 4 squared is 16, 3 times 16 is 48, it's already bigger than 40. And it doesn't matter what x is, just having y be 4, you're bigger than 40. So we know now that any integer y greater than 3 makes the equation greater than 40. So what that means is all we got to check are the integer values from 1 to 4 and 1 to 3, where x is 1 to 4 inclusive and y is 1 to 3 inclusive. Every other positive integer will generate a non-solution. So that's what we've shown to this point. So that reduces our cases to just a table of 1 to 4, just reduces our cases to 12 cases. So each case will be an XY combination. So there's 4 X's, 3 Y's, that's 12 cases. Good. So what it did is created a table. Here are my X values, and here are my Y values. And essentially in these boxes will be what you get when you take the X value and the Y value and you plug into the 2x squared plus 3y squared equals 40 equation. So if I plug 1 in for y and 1 in for x, then 2x squared plus 3y squared is 5. Okay. If I plug 1 in for y and 2 in for x, I get 11. Okay. If I plug 1 in for y and 3 in for x, 21. Plug in 1 for y, 4 for x, 35. Then go row 2, plug in 2 for y, 1 for x, 14. Plug in 2 for y, 2 for x, 20. Plug in 2 for y, 3 for x, 30. Okay. Plug in 2 for y and 4 for x, 44. So far, none of them have hit 40. So none of those XY combinations are solutions. Plug in 3 for y and 1 for x, 29. Plug in 3 for y, 2 for x, 35. Plug in 3 for y, 3 for x, 45. Okay. Plug in 3 for y, 4 for x, 59. And there you go. Notice none of them are 40. So I already know that if x is bigger than 4, you'll never get 40. And we already know if y is bigger than 3, you'll never get 40. That means the only values of x and y that are left to check are 1 through 4 and 1 through 3. 1 through 4 for x, 1 through 3 for y, and we checked all those. None of them are 40. So we've proved our original statement, which was that 2x squared plus 3y squared equals 40 has no solution in the positive integers. And our cases are 1, 1 is a case, 1, 2 is a case, 1, 3 is a case, 1, 4 is a case, and so forth. It's put down here, okay. Since 2x squared plus 3y squared is not equal to 40 for x equals 1, 2, 3, 4 and 1, 2, 3, and since 2x squared plus 3y squared is greater than 40 for x is greater than 4 and x is greater than 3, we conclude this has no solution in the positive integers. Okay. Another kind of proof is a proof of equivalence. Some theorems are of the form P if and only if Q. Such theorems are proved by using this equivalence. P if and only if Q, if you recall in the logic section again, we studied that P if and only if Q was logically equivalent to P implies Q and Q implies P. Okay. That is, so if I want to prove a statement, P if and only if Q, then I need to prove that P implies Q. In other words, if P then in Q is true or is proved, and then I reverse it, prove if Q then P. Okay. So let's look at this case example. Prove that for every integer n is odd if and only if n minus 1 is even. Okay. So first we're going to, in this example, P will be n is odd, right? And Q will be n minus 1 is even, right? Because we're saying n is odd, P, if and only if n minus 1 is even Q. Okay. So first we're going to prove P implies Q. That is, if n is odd, then n minus 1 is even. So prove that first. We can do direct proof on that. Because if n is odd, then n is 2k plus 1, and k is an integer. Okay. So what's n minus 1? N minus 1 is n, which is 2k plus 1, subtract 1, which cancels the 1s. You end up with 2k. And that's our definition of an even number, 2k where k is an integer. So if n is odd, we showed that if n is odd, n minus 1 is even. Okay. Since it's if and only if, you have to show the reverse. You now got to prove that Q implies P, which is Q, remember, was n minus 1 and P was n. So if n minus 1 is even, then n is odd. Okay. So how do we prove that? Direct proof again. If n minus 1 is even, then n minus 1 can be written as 2k. And then all I got to do is add 1 to both sides. Now n is 2k plus 1. And that's our definition of an odd number. So if n minus 1 is even, if n minus 1 is even, then n is supposed to be even, not n minus 1. That's an error there. I'm sorry, if n minus 1 is even, then we're saying n minus 1 is 2k. That's correct. Then I add 1 to both sides. So now n is odd. So we proved if n minus 1 is even, then n is odd. Okay. Here's another one. Prove that for all real numbers x and all positive real numbers d, if the absolute value of x is less than d, if and only if x is greater than minus d and x is less than d. Okay. So suppose we let x be an arbitrary real number and d be an arbitrary positive real number. We must show that if x is less than d, then x is between negative d and d, and then show the reverse. If x is greater than negative d and less than d, then absolute x is less than d. Okay. So remember, absolute x is defined in terms of cases, right? So to show that absolute x is less than d, then x has got to be greater than negative d less than d. Okay. So we assume that absolute x is less than d. So if x is greater than or equal to 0, because remember, the definition of absolute x is equal a number if x is equal to the number, or absolute x is less than a number if x is positive, then absolute x is x, and if x is negative, then absolute x is negative x. That's our basic definition of absolute. So it's a piecewise function, so that's why it has two cases. So if x is greater than or equal to 0, so we're gonna start with the assumption that, so we're gonna prove this. If x is less than d, then x is between negative d and d. So if absolute value of x is less than d, if x is greater than or equal to 0, then x is going to be greater than or equal to 0, but 0 is going to be greater than negative d, because d is a positive number, remember. Okay. So we know right away it's going to be greater. So we know absolute x is going to be greater than d, and it's going to be less than d. Okay. If x is less than 0, then 0 is less than a negative x. Okay. But still greater than negative d. So therefore, absolute x is less than d. So that is negative x is between negative d and d. So we proved it for both cases. If x is positive, then it has to be bigger than negative d, and then x itself is equal to absolute x, which is less than d. If x is negative, then negative x is equal to absolute x. So that's going to be negative x equal to absolute x less than d, and negative x would still have to be greater than negative d. So negative x is between negative d and d. So multiplying by -1, we obtain d is greater than x greater than negative d, and then remember, you can just reverse that around, and now x is greater than negative d less than d. So this proves that if absolute x is less than d, then x falls in there. Okay. Now you got to show the other way around. You got to show that if you know x is greater than negative d and less than d, then absolute x has to be less than d. Okay. We'll assume that x is greater than negative d and less than d. If x is greater than or equal to 0, then absolute x equals x, which is less than d. If x is less than 0, then absolute x equals negative x. And since negative d is less than x, we may multiply by -1, and d is greater than negative x. And combining the fact that absolute x equals negative x and d is greater than negative x, we get absolute x equals negative x less than d. In either case, we prove that absolute x is less than d. So that completes your proof. Okay. So now you've shown it both ways. Okay. It's called, so when you do an if and only if proof, you have to break it into the two cases. If P implies Q, and then prove that, and then you got to switch around. If Q implies P, you prove that. Okay. How do you prove an existence proof? Okay. So remember, there exists x, P of x means there exists at least one number x such that P of x is true. That's called an existence proof. To prove an existence proof, all we need to do is find one number A in the domain of disclosure where PA is true. In other words, you just got to find one case that works, and then you've proved the existence. So, for example, let A and B be real numbers with A less than B. Prove there exists a number X satisfying X is between A and B. So we know A and B are real numbers. We know that A is less than B. And we want to prove that there's some number X, just got to find one that's falling between A and B. So in other words, if I know A and B are real numbers and I know A is less than B, I want to prove it for sure there's a number between A and B. And only got to find one number that satisfies this equation. The number I'll use is the midpoint. Remember, the midpoint between two numbers is the sum of the points divided by 2. Since it's a midpoint between A and B, this is guaranteed to be greater than A and less than B. So there's my one example. That's all I had to find. So it'll work for any value A and B that satisfies the fact that A and B are real numbers and A is less than B. Right? So in other words, say A is 3 and B is 4. Or better yet, say A is 2, B is 4. 2 plus 4 is 6, divided by 2 is 3. 3 is the midpoint between 2 and 4. It's guaranteed to be there. So for any A and B, where A is less than B and they're both real numbers, if I add them and divide by 2, I got the midpoint, the distance, halfway between them. So I'm guaranteed, no matter how close they are together, I'm guaranteed to find a number in between them. And that's all I have to show. I found one number, the sum of the two A and B divided by 2. So that's how you handle an existence. So if you see any question that says prove there exists something such and such, just find one case that works and you're done. Here's another example. Prove that there exists a prime P, right, such that 2 to the P minus 1 is composite, meaning not prime. Okay, so remember, a prime number is a number that's divisible by itself and 1 only. So for example, 3 is prime, right? Because you can only divide 1 into 3 and 3 into 3. So what you do is you're just trying to find a prime number where when you take 2 to that prime number, subtract 1, you get a number that's not prime. Okay. So you just start at the beginning. 2 is prime, 2 squared is 4, minus 1 is 3. Well, that's a prime. The 3 is a prime number. So then you try 3. 2 cubed is 8, minus 1 is 7, prime number. Then what's the next prime up? 5. 2 to the 5 is 32, minus 1, prime. Next prime after 5 is 7. Anyway, keep doing that until you hit one that works. The one I hit that worked was 11. So 2 to 11 minus 1 is going to be composite. 2 to 11 minus 1 turns out to be 2048. Is what 2 to the 11 is. Minus 1 gives me 2047. And it turns out 2047 is the product of 23 and 89. So 2047 is not a prime number, because it can be divided by 23 or 89. So since we said there exists a prime P such as true, only got to find one. There's probably an infinite number of them, but I only need one to prove that statement, and that one is P equals 11. So that's how you attack an existence proof. Okay, so that is it for this lesson.